Hello class, this is Stat 1200. I am your instructor, William Buellman, and today we are covering section 3.2, Measures of Spread. The objectives for today are to be able to compute the range of a data set, compute the variance of a population and for a sample, compute the standard deviation for a population and a sample, use the empirical rule to summarize data that are unimodal and approximately symmetric, and then to compute the coefficient of variation. So first we have the range. The range of a data set is the difference between the largest and smallest value. Although the range is easy to compute, it is often not used in practice. The reason being is the range only involves two numbers from the data set, the largest and the smallest. Here we're going to just do a quick example. So during the semester, a student took 5 exams. The population scores are 80, 83, 95, 68, and 85. Find the range. The highest score is 95. The lowest score is 68. We just subtract those and we get 27. So the range is 27. Again, easy to compute, doesn't give us a lot of information. Another example, we're going to find the range again, this time just with a little bit bigger data set. Again, we look at the highest value, which is 27, the lowest value, which is 12, and we just subtract them, and we get the range is 15. Again, a little bit bigger data set, but still it's a very quick computation. Now we're going to talk about the variance of a population and a sample. When a data set has a small amount of spread, most of the values will be close to the mean. When a data set has a larger amount of spread, more of the data values will be farther away from the mean. The variance is a measure of how far the values are from the mean. So the variance is computed slightly differently for populations and samples. So we're going to look at the population variance first. For population variance, we're going to let x1, x2, x3, and so on denote the values in a population of size n. Let mu denote the population mean, so the population variance is going to be sigma squared, so that's sigma right there, which is equal to the sum of the xi's minus mu, the mean, squared over n, the number and the sample size. Example 3, compute the population variance for the San Francisco temperatures. So here are the temperatures in San Francisco for January, February, March, April, so on. So in order to calculate the variance, the first thing we need to do is calculate the mean because we don't know it. So since it's a population mean, it's mu, which if we remember from 3.1 is the summation of the xi's over n, which is going to be 690 divided by 12, which is equal to 57.5. So now we have the mean. So now step 2, for each population value xi, we need to subtract the mean from it. So here, that's what we're going to do next. So if we do 51 minus 57.5, we get negative 6.5. 54 minus 57.5, we get negative 3.5, and I'm just going to fill in the rest of these. And as a reminder for the last one, so we do 52 minus 57.5, which gives us negative 5.5. So now we've done each value minus the mean. So now we need to take each one of those and square them. So you see the second row here, I'm just going to fill it in real quick since we already have it. and then we'll start working on a third row. See, the second row is filled in, so now we're just going to square those. So if we take negative 6.5 and times it by negative 6.5, we get 42.25. Negative 3.5 times negative 3.5 gives us 12.25, and continue on filling in the table. Now we have all of them squared, so our next step is we have to sum them together, which we will see in the next slide. Now we're going to sum them all together. So we have 42.25, which was the first one, plus 12.25, which was the second one, plus 6.25, which was the third one, and we're going to keep doing that, so I'm just going to put dot, 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 all the way to the last one, which was 30.25, and if we add all of those up together, we get 169. We have everything we need, so now we're going to plug it into this sigma squared, which was the summation of the xi's minus mu squared over n, which we have is 169, right? Because that's what we have up here in step 4, and there was 12 values, which gives us 14.083. We normally round to 3 decimal places unless told otherwise. So the population variance is 14.083. Now we're going to do the sample variance. When the data values come from a sample, rather than a population, the variance is called the sample variance. The procedure for computing the sample variance is a bit different from the one used to compute the population variance. In the formula, the mean is replaced by the sample mean, so the mean for a sample is x bar instead of mu, and the denominator, instead of being capital N, is n minus 1. The sample variance, instead of being sigma squared, is just s squared. You may ask, why do we divide by n minus 1? If the population was just n, why is the sample n minus 1? When we compute the sample variance, we use the sample mean to compute the deviations. For the population variance, we use the population mean. It turns out that the deviations using the sample mean tend to be a bit smaller than the deviations using the population mean. If we were to divide by n instead of n minus 1 when computing a sample variance, the value would tend to be a bit smaller than the population variance. So we can show this mathematically if we wanted to, but that's not what we're going to do in this class. It's just something you're going to want to remember. I'm going to do an example of sample variance. A company that manufactures batteries is testing a new type of battery designed for laptop computers. They measure the lifetime in hours of 6 batteries, and the results are 3, 4, 6, 5, 4, and 2. Find the sample variance. So first, again, we have to find the mean. So we're going to do that first. And remember, x bar is equal to 3 plus 4 plus 6 plus 5 plus 4 plus 2, all divided by 6, which is equal to 4. So, and sample variance is the summation of the xi's minus x bar squared over n minus 1, which if we do that, we have 3, the first value, minus the sample mean, 4, squared, plus 4, the second value, minus 4, squared, plus, continue on, to 2, the last value, minus 4, the mean, squared, all over n minus 1, which is 6 minus 1, which when we do all that math, we get 10 on the top, 5 on the bottom, and 10 divided by 5 is 2. So our sample variance, which is s squared in this case, is 2. Now we're going to do standard deviation of a population and a sample. Because the variance is computed using squared deviation, the units of variance are squared units of the data. So it's a squared unit for variance. For example, in the battery lifetime example, the units that we got were hours, so the variance units were squared hours. In most situations, it's better to use a measure of spread that has the same units as the data. So since our original data was in hours, we want a measure of spread that is also in hours, not squared hours. We do this just by taking the square root of the variance. And we call that the standard deviation. The standard deviation of a sample is denoted by little s. And the standard deviation for a population is noted by, this should be sigma right there, not little s. So sample standard deviation is s, which is equal to the square root of s squared, and population standard deviation is sigma, which is equal to the square root of sigma squared. So both of these are just saying that the standard deviation is just the square root of the variance. Back to our temperature example for San Francisco, we had that the variance was 14.083. Find the standard deviation. So the standard deviation, which is sigma, is equal to the square root of sigma squared, and we already know what sigma squared is. It's that 14.083. So if we take the square root of 14.083, we get the answer is 3.753. So our standard deviation here is 3.753. If you notice, I didn't give you units in the other one, so that's why there's no units here. But typically your examples would have units, and this would have an answer of units, but in this case I didn't give you one. Variance for the lifetime for the sample of 6 batteries was 2. Find the sample standard deviation. So again, standard deviation, in this case s, is just equal to the square root of s squared, which is equal to, we already know, square root of 2, which is equal to 1.414. So we can see once we have the variance, finding the standard deviation is very simple. It's calculating the variance that takes a while. I want you to recall resistance. So recall a statistic is resistant if its value is not affected much by extreme values, either very large values or very small values. The standard deviation is not resistant. That is, the standard deviation is affected by extreme values. So you need to remember that the standard deviation is not resistant and can be affected by extreme values. So now we're going to talk about bell-shaped histograms. Many histograms have a single mode near the center of the data and are approximately symmetric. We call these types of histograms bell-shaped. If we have a data set that we know has a bell-shaped histogram, it is often possible to use the standard deviation to approximate the description of the data using a rule that's called the empirical rule. And what the empirical rule says is approximately 68% of the data will be within one standard deviation of the mean. Approximately 95% of the data will be within 2 standard deviations of the mean. And all or almost all of the data will be within 3 standard deviations of the mean. But remember, this only works if the data has a bell-shaped histogram. We cannot use the empirical rule if the data does not have a bell-shaped histogram. This little graphic shows us here if we have a population mean mu in the middle that 68% of the data should be within 1 standard deviation plus or minus. 95% of the data should be within 2 standard deviations plus or minus. And almost all of the data should be within 3 standard deviations plus or minus. So this is just a way for us to visually see what we're talking about. Example 7, the following table presents the U.S. Census Bureau's projection for the percentage of the population age 65 and over for each state and District of Columbia. Use the empirical rule to describe this data. So I'm telling you to use the empirical rule so you can. The mean of this data is 13.25 and the standard deviation of this data is 1.68. Remember, to use the empirical rule, we care about 1 standard deviation, 2 standard deviations, and 3 standard deviations. Minus sigma, we have 13.25 minus 1.683 and 13.25 plus 1.683, which gives us 11.57 and 14.93. So that tells us approximately 68% of the data values are between 11.57 and 14.93. So now we're going to do for 2 standard deviations. So again, the mean hasn't changed, still 13.25. Now minus 2 times the standard deviation of 1.683 and plus 2 times the standard deviation of 1.683. When we do those calculations, we get 9.88 and 16.61. So approximately 95% of the data values are between 9.88 and 16.61. So now similarly, we're going to do 3 standard deviations. So we have, again, mu is 13.25 minus 3 times the standard deviation plus 3 times the standard deviation. Doing those calculations gives us 8.20 and 18.30. So almost all of the data values are between 8.20 and 18.30. So that's a way we can use the empirical rule if we know mu and sigma, which are the population mean and the population standard deviation. We're going to take those values we found and fill them in. So we have 8.20, 9.88, 11.57, 13.25, 14.93, 16.61, and 18.30. So here's just the graph of the empirical rule with the data values filled in. The last thing we're going to cover on this section is something called the coefficient of variation. The coefficient of variation, which we're going to call CV for short, tells us how large the standard deviation is relative to the mean. It can be used to compare the spreads of datasets whose values have different units. So our coefficient of variation is used when we have 2 different datasets or more, and we just want to figure out which one is more spread out compared to the other ones. So we don't really need to know the units, we just want to figure out how spread out the data is. So to find the coefficient of variation, CV, it's just equal to our standard deviation divided by our mean. Here's our last example, example 8. The National Weather Service records show that over a 30-year period, the annual precipitation in Atlanta, Georgia has a mean of 49.8 inches with a standard deviation of 7.6 inches. And the annual temperature has a mean of 62.2 degrees Fahrenheit with a standard deviation of 1.3 degrees, also in Fahrenheit. Compute the coefficient of variation for precipitation and for temperature, and tell me which one has the greater spread relative to its mean. So we can see that these have different units. Precipitation is in inches versus temperature is in degrees, but a coefficient of variation gives us a way to compare which one is more spread out, even though they have different units. So first we're going to find the coefficient of variation for precipitation, which is going to be equal to the standard deviation of precipitation over the mean of precipitation, which we were told was 7.6 over 49.8, which gives us 0.15, and our coefficient of variation for temperature is equal to our standard deviation for temperature over our mean for temperature, which is 1.3 over 62.2, which gives us 0.02. So now we found the coefficient of variation for both precipitation and temperature, and now we can just compare the two numbers. For temperature, we have 0.02, and for precipitation, we have 0.15. So all we have to ask ourselves is which one of those is larger. That will tell us which one has the greater spread. So since the coefficient of variation for precipitation is larger, it has a greater spread than temperature. So I'm just going to write that down. So down here at the bottom, you can just see that I wrote down what I said in words. Since the coefficient of variation for precipitation is larger than the coefficient of variation for temperature, we say that the precipitation has a greater spread relative to its mean. So that's what coefficient of variation is used for, just as a measure of spread.